Regional Hazards Coordinator for the USGS Pacific Region and Region 9 Chair of the Department of Interior Regional Emergency Coordination Council. Try to say that 10 times fast. Michael Dettinger, we'll call him Mike. Mike is a research hydrologist for USGS and a research associate at the Climate, Atmospheric Sciences and Physical Oceanography Division at the Scripps Institution of Oceanography. Try to say both of those fast. So yeah, so let's bring them both up with a warm round of applause.
Mike Dettinger's shy.
No. Just, I'm not talking for later.
Yeah.
Okay.
We'll start.
I wanted to see your size.
Pop that in.
Can you hear me?
Yes.
Try to. Now, I have massive PowerPoints, so this PowerPoint is like 350 meg. It's bound to crash. Just going to tell you that's right now. I'm here to talk about ARkStorm, and ARkStorm is a scenario, but first I need to talk about what it is that we do at the U.S. Geological Survey. And really the USGS doesn't manage or regulate anything. We just basically provide sound science to the public, to policymakers, and people that have to make hard decisions, and hopefully that science holds up in court and carries the day, because what I'm focused in and all this stuff here is the natural disasters. One of the things that we really work for is to save lives and property. A little bit about multidisciplinary science, and I have to do this because I've been spending the last 15 years doing this, is trying to bring science together within the USGS. I've seen a couple of scientists here, and they can tell you that science tends to stovepipe, you know. I mean, you're working as an ecologist in alpine systems, and you're going to be around other ecologists in alpine systems. And I had to cross the divisional lines, and in the USGS, they were really divisional lines. One of the first big projects that I did up here was the mapping of the bottom of Lake Tahoe. And that was to bring in our scientists that do oceanography, to bring up Dr. Tahoe, really to give the ecologists a better idea of what's down there so that they can know where fish live and many other good things. But then the next thing that I did was, gee, what happens when you take up concrete in the LA River? I mean, LA, you've probably seen Arnold Schwarzenegger driving down the aqueduct system there in his motorcycle, or if you're watched Grease, etc. This place is as dry as a soda cracker. You start reintroducing tertiary treated wastewater in this system, and you might have liquefaction in the event of an earthquake. You might be reintroducing these pharmaceuticals and drinking water into an aquifer system, and there's a lot of issues that you need to deal with. And this was really one geared for a USGS that deals with geology, water, biology, and geography. So, natural hazards in the Pacific region. I'm a regional hazards coordinator. Most of this stuff is dealt with. And by the way, I don't have volcanoes up here. I've left that out for some reason. I don't know why, because it's a big issue for me right now. But it's earthquakes, fires, floods, landslides, debris flows, tsunamis, coastal change. The Pacific region is California, Nevada, Hawaii, all the way out to the Pacific Islands in Guam, Kwajalein, etc. And there's a lot of stuff that we do as a matter of course. If there's an earthquake, you can go on our website and you can see exactly where that earthquake happened, where the shaking occurred, and how many people were affected, the economic hit, and how many fatalities could happen. And then we give you that information within about 15 to 20 minutes. That's a pretty good deal if you're an emergency manager. You know where to go and you know not where to go. So this is a really good idea, so that we turn this into a multi-hazards approach. And we started by the way, this ditch is what, 6 geologists high? Okay, that's good. Okay, we brought all these emergency responders together and say, hey, how can we have science help you? You know, and they kind of look at each other and they're like, well, we're not scientists. We don't know what you guys do, and you know, unless we're scientists, we don't know. And so this guy here, Larry Collins, he's the captain of Los Angeles County Fire Department, Urban Search and Rescue. a very photogenic guy, as you can imagine, in LA. And he says, you know, we do disasters as a matter of course. It's the catastrophes that take us by surprise. If you can help us with the disasters, we'll do the catastrophes that much better. Or, no, if you do help us with the catastrophes, we'll do the disasters that much better. And I got that. Because I think I crafted that quote for him. I said, come on, do it again, you know? And he was the one that says, you know, everybody talks about the big one in Southern California, but I've never actually worked a big earthquake. I mean, I went down to Mexico, and you know, they had me do here and here and here. But we had all these young guys. And then, you know, we had the older guys who worked on Northridge who think they know it all, but really Northridge only, you know, was an earthquake that occurred if 7 seconds of shaking. A 7.8 would take about 2.5 minutes. I mean, this is a big deal. If you were talking about this room shaking that much, I mean, you would have this thing here, and then a second later over here, and then back again over here. You know, I mean, it'd be like that for 2.5 minutes in some areas. So they aren't really prepared to deal with that. So what we decided to do was to put together an earthquake scenario, and then also look at the fires. And so we coordinated the Southern California firestorm, and then also put together a tsunami scenario, which is still going on, and then a winter storm scenario. But the first thing that we did was the ARkStorm, excuse me, the shakeout scenario. Now I got to tell you, the fearless leader of this is Lucy Jones. And if you go into Southern California, there's stars everywhere in LA. But you walk around with Lucy, and she is a major star. Because if there's an earthquake, you turn on that television, and who's going to be there? You're emotionally invested in this whole ordeal, and this is the woman that is talking to you. She's one of Time's 50 most influential women. And she is the leader of this. I was a project manager on all of these things, and supervisor of staff scientists. And we have a whole list of people that were participating in this that were dealing with the physical aspects of it, the engineering, and then the social and economic concerns. A lot of people. So, an earthquake scenario, at its very least, this is an earthquake scenario. This is the type of shake map that you will see after an earthquake. Within 5 minutes after a major earthquake, hopefully you won't see one that looks like this. But you'll see in the Mercalli scale, and it'll have in there how much peak ground acceleration and all that. But you don't really care. All you need to know is this red here. That is enough to bend steel rails. Okay, so that is some intense shaking. And so this blue here, that's the P wave. That's the one that when it hits, you go, oh, hey, was that an earthquake? That's kind of cool. Okay. So we had to pick an earthquake. In the scenario, we picked a 7.8 earthquake. That means that this area of the fault had not moved for about 300 years. So this area down here, this had moved in about 150 years. But every section of the San Andreas Fault tends to move in about every 150 years. So this would be a good one to pick if you're going to pick one. Now, we chose it to happen at 10 o'clock in the morning. Why did we choose that? Because everybody would be working that day. This is going to be on a Thursday, November 13th. Kids would be in school. A lot of people work on this side of the fault, this side of the fault, and live on this side of the fault because it's too expensive to live over here. This was an earthquake that started here and moved this direction, started at Bombay Beach, moved to Lake Hughes. Now, this is a little bit of how it works. You can see that the earthquake has just now happened. So this is going to be in real time. It started down here. You can see the shaking. Can everybody see that? Now I got to tell you this. This is Dodger Stadium. This is the Coliseum down here. Here's downtown. Here's Disneyland over here. And Palm Springs is toast. And the people in LA don't even know it at this point. Okay, now you've got to get your mind around this. If you're an emergency manager, you have assets that you have to deal with down here, and you don't even know about it yet. So you can see this thing moving. Now this is exaggerated 1,000 times, but you're way up. So look, the P wave is coming through, and you go, whoa, I think that was an earthquake. That's kind of cool. But you don't know exactly what is happening at this point. And it hasn't even happened in LA, but you can see it coming this direction. But this is generally how these earthquakes happen. And this is blowing a lot of people's minds because they still have that pebble. You drop a pebble in, you see the waves going outward. But really, it pushes the energy out into this area. What happens here in Southern California is you have this plate that is moving against another plate. It pushes up the San Gabriel Mountains, and then the fires and then the rain washes it down, and you create all of this sediment down here, which is great for agriculture, and that's why so many people live there. But you can see, okay, here comes these really intense waves. It's hitting downtown. In this scenario, we had 5 high-rise buildings that came down. It was very controversial. Believe me, the engineering institutes and all the others are going, what? You can't do that. But we worked with 300 scientists on this thing, and we had to have it done at a particular time because we wanted everybody to be on the same page with this scenario. And that means kids in school doing a drop, cover, and hold exercise. We wanted the emergency managers all doing something on that day called the Great Shakeout. And we were going to have it on that November day. We chose that day because it was after the election and it was before Thanksgiving. And nobody was going to pay attention to it if it was during an election, but the sociologists told us if you really want to make people change, you have to get them to talk about things that are important to them with the people that they love. And so we're going to get people together on Thanksgiving. And so if you're doing this thing in school and saying, hey, Mommy, I did this thing in school today, and, Mommy says, hey, we did something at work too, that would be cool. And so that's what we were shooting for. And that happened in November 13th, 2008, and just to make things more difficult for me, I started the winter storm scenario on October 28th, which was a couple of weeks before that. Mike was there, and we started talking about what would be a winter storm scenario. And I'm going to change out of this. By the way, Shakeout is now an annual event, and we wanted to do it like they did it in Japan, and now Japan is actually doing the Shakeout. It's kind of a cool thing. So we needed, well, first we were talking about just doing a storm scenario down in Southern California, and Mike said, I will pull out of this and not be involved with it unless it involves things in Northern California, and I was all for that myself too. So we knew that this big storm had happened in 1861 and 1862. We don't have a lot of knowledge about it. There's only a couple of rain gauges out at that time. Some stream gauges that were out and about, but those had to be done, in a strange way of going back and basically doing hydrologic forensics of that's what I'll call it because I'm not going to get into the hydrology of that. And but we do know that it was a large storm that flooded most of California, bankrupt California. The governor, Leland Stanford, had to take a rowboat to his inauguration. And that we needed to make it science-based for anyone to believe it, like the Shakeout. The Shakeout was completely based on science. And we'd have one realistic outcome, like we just picked Shakeout. Okay, this is the way the Earth is going to be. Everything's going to fall in place. That's why we're going to do the same thing on this one. And then we'd look at the environmental excitations, physical damages, and then social and economic consequences, just like Shakeout. But the deal is that we have to make this so that people can believe it. So it can't be as big as 1861, 1862. We have to dial it back. This was prior to Tahoe. Okay, so you've all seen big disasters. But you did not see that when we first started this. You did not see Frankenstorm, which, by the way, if you type in Dale Cox and Frankenstorm, you'll see that I said that word in 2010. So here's how the scenario will work. We start with the meteorology. It had to be scientifically based, very plausible. We pulled together an A-team to do this, including people from DRI, Kelly Redmond, and Mr. Atmospheric River, which I'll get to here in a second, Marty Ralph from NOAA, ESRL, Mike Dettinger, Dan Cahan from Scripps, a whole host of the best and the brightest meteorologists. And I told him it has to be a plausible scenario because everything else is going to rest on top of it. Now, what we didn't have in Shakeout was this, the forecasting element. And that'll come in later. So a little bit about 1861, 1862. Flooding 300 miles wide, 12 to 60 miles wide, miles long, 12 to 60 miles wide. LA Basin generally inundated. San Gabriel, San Diego rivers cut new paths to the sea. The largest community between LA and New Mexico, Agua Manza, which ironically means smooth water, is completely obliterated. The only thing that is left is the church house steps. And those are a historical artifact because that's how they figured out how much water came down the Santa Ana River, because it went to the church house steps. They thought they were completely gone, and then it was some archaeology. They discovered that there they were. And so now they're getting a better idea of how big that was. And it was 2 storms separated by 12 days of not so much rain. Now, at this time, because of climate change, it's really screwing up our way of getting to flood frequency. There's something called non-stationarity, meaning that when you look at you go back in the period of record, you say, okay, well, here's 50 years of period of record, then you can expect this big of a storm. But climate change is kind of throwing a little monkey wrench in the mathematics of that whole thing. And so, really, to make this strong, we went back and looked into what's called the paleo record. And a couple of people, Arndt Schimmelman from the University of Indiana, Lynn Ingram, who co-authored a recent article in the Scientific American with Mike Dettinger. I don't know if anybody has seen that. It's a very good article with great graphics. And they have shown that there was these mega floods that happened in 212, 440, 603, 1029, 1418, and 1605, generally about 200 years apart. The 1861-1862 storm did not even register in this. These are megastorms. And this is a quote from Arndt: "We foresee the possibility of historically unprecedented flooding in Southern California during the first half of the century." Based on this information. So that, so this is what we did. By the way, this is what an atmospheric river looks like. You may have heard of the Pineapple Express, and that's one subset of an atmospheric river. And this is really where Mike should probably start talking, since he was the one that sort of led he did lead the meteorology of this. But I just wanted to give you an idea. You experienced one of these if you lived in Tahoe or anywhere in California around this area about the end of November, beginning of December. And generally, this is, Mike, is this your graphic? Okay. So when we deal with hazards, meteorological hazards, mostly what we're dealing with here is atmospheric rivers, blizzards here, tornado alley, and then hurricanes and tropical storms. The interesting thing about this, for people that say it doesn't rain in Southern California or California in general, here's 3-day totals of precipitation. Most of the precipitation that comes into California we use for, and these big storms account for about 50% of the precipitation. It's a big thing, but it's about 100% of the calamity associated with floods and hazards. And so we looked at this 1861 storm and tried to recreate it a little bit, made a storm analogous to it. So we pulled together 2 known storms, 1968 and 1969. Now I got to stop here because everybody, if you're in the meteorology or if you're in the hydrology, you talk in terms of 1969, 1986, and people glaze over. Like, well, I wasn't actually born at that time. So unless you're a hydrologist, or you're not going to know. And so we decided to call this an AR-1000, or I made up that term. And we were working with the Art Center College of Design. First, they were going to brand it. They branded our shakeout for us and all this kind of stuff. And they're going, okay, we're not going to tell you what it's going to be called until you guys all come down here. So I had all the scientists, all the people working on it come down to Pasadena. Most of the automobiles that are designed in the world are designed from graduates from the Art Center College of Design. They know how to brand things. They know how to design things. Okay, so we're there, and they go, it's going to be called Killstorm. And I pretty much lost every one of the scientists that were going to work on this. So anyway, we used 1969, which was a big storm, and 1986. One tended to focus on Southern California, but it still had impacts to Northern California, and the other ones in Northern California, but had impacts in Southern California. Now, these atmospheric rivers are the sort of thing that you will probably be seeing with climate change. You don't have to read this whole thing. It's just basically what you can expect from climate change in the West is extended periods of drought, higher temperatures, and sea level rise, and more frequent and ferocious storms. So we had this great data set. It involved I had all of the precipitation data. It had temperature, winds, wind direction, barometric pressure. We had to figure out, well, given a storm this size, where did the landsliding occur? How much is there going to be in coastal erosion and inundation? So we had to create all this new science to figure that out. So doing these scenarios leads to new science. This landslide susceptibility map was never before created. That is now going to go into that one thing I showed you where the shake map, so that you can say, given the shaking, it's shaking now, where the landslides are supposed to happen. Emergency managers, Caltrans, or NDOT, go here, not here. And for the modeling for the coastal change, we've added a sea level rise in there, so it's not just like this bathtub thing. It's more like it doesn't have to rise all that much, and you still have a big storm, and it's going to be a much bigger calamity for you. And it's a big deal. So we turned. I don't want to get into much on how we turned this into floods, but it was a very kludgy way. But just know that this precipitation turned into this floods. And that is about 300 miles long, 12 to 60 miles long, wide, and that looks very much like 1861, 1862. Let's see. It overwhelms the state's flood protection system, very much like 1861, 1862. Winds, the winds that are associated with this it's a wind disaster, but it's a flooding catastrophe. And there's hundreds of landslides. And and then you get into the depth and duration of this sort of storm. I went and showed this to Mark Bendavoya, the captain of, or the chief of the Sacramento Urban Search and Rescue, which is, his district is right here. I mean, that's his quote. Sums it up. Here's the Bay Delta. Now, this is a huge issue for the Bay Delta because we've overtopped the levees. No, this is okay. You're just flooding all this fresh water in. They can still pipe fresh water down to Southern California, but the levee system is compromised. They only have 6 months to fix it. They only have one barge big enough to do that. And these are the sort of things. So when I showed you the shaking there in Southern California, I showed this to the dam operators down in Southern California, and I showed them that shaking, and I said, okay, how many of your dams are going to fall down? It's quiet. So how many of your dams are going to have cracks and fissures? Oh, all of them. Oh, okay, well, what do you do when you have cracks and fissures? Well, we let the water out. All at the same time? Well, these guys are kind of competitors. They don't really talk about this sort of thing. How do you make that decision to let the water out? Oh, well, we have blackberries. They're not going to work, Cell phones don't even work after a major marathon in San Francisco, So, and you guys are going to have to come. So this is the sort of this fragility of interdependencies. So, and this is the same thing we saw here. You cut the natural gas. By the way, everything that comes into and out of Southern California crosses the fault. You've cut the major lifelines that go in. You cut the natural gas lines, and there goes your public transportation. You don't have public transportation, nobody's going to come to work. You're not going to get the businesses back going. All these small businesses, which you have a lot of in in Tahoe area, they can't last that long. And this is what we saw in the Bay Delta too. So in a sense, this was a $750 billion damages, a shakeout. And by the way, there was environmental concerns. I'm going to kind of blow through this. By the way, here's sewage treatment plants. So this is how big it is compared to earthquakes in the scenarios. Ours was 750. The flood. So you're talking about the big one? This is the big one. This is what it looked like to Katrina. When you take in all of the physical damages, you look at the business interruption, it's nearly $1 trillion. So, California's flood protection is not designed for it. I'm not going to talk about Nevada right now. If you plan for an ARkStorm, you can be planning for an earthquake as well. Flood mitigation should consider an ARkStorm, as a way to look at what would happen to your community. And it does not, I'm just going to leave it here, it doesn't have to be a catastrophe. Here's where we're going. Okay, so Shakeout turned into a big deal. It's global now. We had 19 million people doing Shakeout last year. I called this, sort of a way to get the everybody into, I call it an Atmospheric River 1000 as a way to sort of scale it. Dettinger and Marty Ralph have come up with another way of scaling storms, which Mike can probably talk about. We came up with these maps that I talk about. Multi-hazards demonstration project, which I was the project manager of, is now a national concern. We've got the 21st Century Western Observing System coming in to look at these atmospheric rivers. Navy and NASA used it in 2011 as the basis of their full-scale disaster exercises. Ventura County, San Diego did it this year, and Kelly and may be doing it in 2013, and then we are hoping to do this at Lake Tahoe. And
we are doing it at Lake Tahoe.
Doing it in Lake Tahoe. We are going to do it in Lake Tahoe. I'm hoping. We just had our first big meeting today, and that's why Mike and I are up here. And it was led by Maureen. Thank you, Maureen, the Executive Director of the Tahoe Science Consortium. And thank you for that. And so we're hoping that it is not a catastrophe for Tahoe and that you guys can take care of these low-hanging fruit to keep a disaster from going into a catastrophe. Here's a little bit of a movie about it, and then after that Mike will be talking about the science of atmospheric rivers in Tahoe.
California, 1862. It has rained for almost 45 days. Fierce storms have inundated a 300-mile length of the Sacramento and San Joaquin valleys with water. In Southern California, the flooding has drowned thousands of cattle and washed away homes, food crops, and vineyards. The state is bankrupt, and many communities have been ruined and will take years to recover. Research shows that this is not the only big storm of our past, nor the largest. While the Great Flood of 1862 may no longer be in living memory, a storm of this scale is inevitable once again. This is the ARkStorm. Winter, present day. Weather reports show atmospheric rivers of moisture forming in the tropics, growing larger and gaining speed as they travel towards the west coast. The state braces for the impact of the coming storm, but the public at large does not comprehend the extreme danger the storm poses. The ARkStorm slams the coast with a fury rivaling that of hurricanes, beginning a process of destruction that will last for weeks. Levees and flood control systems are overwhelmed by the incredible volume of water that has nowhere to go. Widespread flooding occurs throughout the state, severely affecting Sacramento, the Bay Delta, Los Angeles and Orange counties, San Diego, and many other communities. Over the course of the storm, as much as 10 feet of rain falls. Thousands of landslides occur, damaging homes, highways, and roads. Property damage approaches $400 billion. Much of the total loss is uninsured, so large numbers of building owners do not have the financial resources to pay for repairs. After almost a month of continuous rain, the storm finally subsides, leaving many parts of the state flooded for months to come. How will society deal with the social, economic, and environmental consequences of this tragedy? Together, we can prevent the ARkStorm from becoming a major catastrophe. How can our government agencies work effectively with one another to create emergency response and evacuation plans so that instead of victims, we would have survivors? What if we could prevent the inundation of major communities through creating more advanced flood controls and levee systems? A heightened level of readiness is essential to averting this potential catastrophe. After all, preparedness is part of our civic duty and obligation to society. To learn more about the ARkStorm and about how you can be part of the solution, go to www.arkstorm.com.
So that's the other thing that the Arts College put together besides the name Killstorm. We like this a lot. So what I'm going to be doing is nerding out on you a little bit, but bringing it home to Tahoe. Talk about what we know about things like an ARkStorm in Tahoe, and then give you a quick view of at least my vision of what an ARkStorm at Tahoe exercise might look like. So Dale showed this kind of animation earlier. I should say what you're looking at here is the amount of water vapor in the atmosphere. And the brighter the color, the warmer the colors, the more water vapor you're looking at. And the big surprise, really it was a surprise about 15 years ago, was that outside of the tropics, the transport of water vapor sort of in the atmosphere is dominated by transport in each day, a few narrow bands of water vapor and water vapor transport that were dubbed at the time atmospheric rivers by some folks at MIT. This is just sort of looping around and around, but you'll see that there are atmospheric rivers on both sides of the equator. There are atmospheric rivers over both, the oceans, and they don't stay in one place. It's not like a river basin where it stays put. They're continually moving and evolving and growing and coming apart. And when when it really gets exciting is when they manage to come over and make landfall. When they come up on the coast and start interacting with mountains and the like. So here we've got a picture of an atmospheric river sort of coming in off the Pacific Ocean over the more or less Monterey area, and then continuing on towards Tahoe here. And as they come, these atmospheric rivers are roughly 400 kilometers wide, which is about 250 miles wide. The core of them, the really intense parts may be much narrower than that, but generally speaking, they're about 400 kilometers wide. And they're much longer than they are wide. We don't call them atmospheric rivers unless they're at least 1,200 miles long. But some of these things will extend from from the west coast all the way back virtually to the Philippines. So they'll go right all the way across the Pacific Basin. And they come in off the ocean about a mile above the surface, the Scientific American didn't like this mixing of units, but as a nerd, the best way I can describe, the simplest way I can describe it is between a kilometer and a mile high. And it's really just about that band. It's about a kilometer to a kilometer and a half or so, but it's a kilometer to a mile high in the atmosphere. And because they're up there, we haven't traditionally been able to see them with instrumentation that we have on the surface. And weather balloons only are set off twice a day at a couple dozen places around the country. And so we really didn't have a good sense of that this was going on. We occasionally come up through one of them and be able to see what was going on. But that was a snapshot, and then we didn't see anything for another 12 hours. And by then it was gone in many cases. But with satellite imagery and with some studies that the folks at the National Oceanographic and Atmospheric Administration did, where they actually flew out into some of our Pacific storms, we started to realize that these are a particularly vicious kind of storm that we deal with all the time here on the West Coast. They happen to be the atmosphere associated with these, the temperature profile is such that they're really relatively easy to lift up. So when they hit a mountain range, they lift up more easily than other winds. And that means that they can go up, cool, condense out precipitation, and boom, you get a lot of rain and snow. And if you ask how much water is in these things, the unit, another weird unit that we like to use, is if you took all the water vapor in typical atmospheric rivers, and condensed it out and turned it into a real river, a land river. The amount of water that's being carried along these things, typically in typical atmospheric rivers, ranges from an amount equal to a rate equal to 10 times the average amount of water that the Mississippi River carries into the Gulf of Mexico, 10 to 20 times that much water. Okay, and so these are carrying a lot of water, and when they get lifted up over the Sierra and the like, you get a lot of water out of them. So, okay, as I promised, my job is to sort of bring it to Tahoe a bit, and now I'm really going to start nerding out. But so, you know, so how do these look when you get to Tahoe? Well, I mean, you know, at a very simple level, these are your basic big warm storms. These are the big ones, and they're warm, so a lot of rain rather than snow in many cases. And as it says up there, on average, atmospheric rivers at Tahoe City in particular, are warmer by 2 degrees C, so that's most of 4 degrees Fahrenheit, and wetter by 85% than wet days in general at Tahoe City. So these really are, on the whole, much warmer and considerably wetter than sort of the rest of your storms. And indeed, another way of kind of looking at that is to ask, here I went and I said, okay, you know, let's look through the historical record from 1948 to 2010 at Tahoe City and look for all the days where the minimum temperature never got below freezing. So if it's precipitating, you're probably getting rain. And the rain was more than 2 inches in a day. So these are big and warm storms. And there were, I don't remember, 38 of these that I turned up. So these are extreme storms. You know, in 60 years there are 38 of these. So I'm way out at the very warm, wet end of the spectrum. And if you look to see what was going on those days, 81% of those historically were atmospheric river storms. So this is, you know, you can almost stop at that point. This is how you get your big warm storms at Tahoe. And here's sort of the seasonality of that. The bars here are how many of such storms happen in each month of the year, and the red part is the atmospheric rivers. And what you see is that really in the winter, if you're going to get one of these storms, it's going to be an atmospheric river. It really dominates things. Now, I don't have a time series of the total amount of stream flow that flows into the river each day. I don't have that. The one thing I can do is just take the water level in the stage, the water level of the lake, and look at that. When you look at that, to me it was really astonishing when I pulled the series for the first time and had a look that I was thinking the lake is quite a big critter, and it seemed to me that, you know, the water levels would rise and fall relatively slowly through time. When you look at it, and it was actually Jeff Schlotto who said, you know, have a look at the big changes. There are often days where the lake jumps a couple inches in a day, and some of these are more like 8 inches that you don't even see among those 76. So, you know, sometimes there's enough water coming into the lake, either from precipitation falling on the surface, well, it's partially from precipitation falling on the surface, or because snow melt or rainfall runoff coming off the sides, that you can jump the level of the lake. I mean, that's a lot of water by anywhere from 2 to, like I said, 8 to 10 inches in some cases. And so I can kind of use that, especially because those often happen in the cool season, so there's not so much evaporation going on. I can kind of use that instead of having measurements of all the flow that's going in the sides. I can watch what the lake's doing. And when I do that, what you can see here already that, so if I look for the case, all the cases, 76 of them when the lake jumped by more than 2 inches in a day, again, you know, over 80% of those days those happened during atmospheric river storms. Yeah. This map sort of is a geeky way of showing that red finger pointing directly at Tahoe is kind of the average atmospheric river that does that. So, you know, it's a geeky way of saying the same thing. There's atmospheric rivers are associated with, you know, very much, to say it's the majority is understatement. It's very much the lion's share are atmospheric rivers. This is how you get the big inflows to the lake. Now, water coming into the lake is one thing. Sediment and nutrients are another, especially if you're to the extent that we're worried about the clarity of the lake, which I think we all are. So I'm going to show you several slides, which are really geeky stuff, but where I'm going to take apart the record of daily suspended sediments coming into the lake from the Upper Truckee basin there. And there's a record that I was playing with that extended from 1971 to 1992. Tim and others got it for me. Tim Rowe at recently of the USGS got it for me. And so what I've done here is on every day in that period, I took the amount of water flowing into the lake at Upper Truckee, and then compared it to the amount of sediment that came in on the same day. And so that's what I'm plotting here. And for the most part, you know, if you get more flow in, you're probably going to be carrying more sediments. And that's what this cluster here looks like. It's just saying more flow, it results in more sediments into the lake. But then there's a bunch of these where if this is the general rule, these are showing much more sediment coming in than you might expect from the amount of flow. This is sort of your muddy inflows sort of day, I think. Okay, and so, you know, I arbitrarily drew a line, and so just look at the days that fall above this line. These are my high sediment load days. There, in that whole period, there are only 36 of these. And you know, only 36 out of this long period, but you know, what this pie chart here is showing is the total amount of sediment on those 36 days compared to the entire period there, maybe, you know, multi-year period there, 20 years sort of period there. And so 36 days compared to 20 years, more or less, is what we're showing here. So these really are a very important input to the lake in terms of sediments, and presumably some, probably nutrients, although I haven't looked at the nutrients into this. So that's the same picture, more or less, there. That's the same thing, just 18% of all the sediments into the lake from the Upper Truckee happened on these 36 days. And it's just comparing, you know, the flow on those days was high, but it amounted to about 4% of the flow during those days versus 18% of the sediment. So we're getting this amplification of the sediment. And the number of days is, of course, virtually minuscule compared to, you know, that 18%. Yeah. So basically, sediment transport into the lake on those 36 days is way out of proportion to the number of days or even the amount of water that was carrying it into the lake. So let me see. So when I show this to some folks, locals, they'll certainly say, well, those are your big rain on snow. Those are your warm, wet storms, right? Well, I already talked about warm, wet storms. So if I kind of go in and focus in and look to see how much, let me see here, how much of the, so I basically chose another one of these setups that's, you know, looking for days that have more than 2 inches of precipitation and never get down below freezing at Tahoe City. And what I find is that, you know, again, sort of it's a very small number of days, but it, you know, it amounts to like 6% of the total sediment into the lake from upper trucking. Point being, it's 30 times as much as an average day would be carrying into the lake. So the point is that, warm, wet storms are a particularly violent way of getting sediments into the lake. So then, of course, you know where I'm going to go with this. Let's go back to atmospheric rivers. So we look at that same 18% and ask, okay, how many of those were atmospheric rivers? And what we see here is that 2/3 of those days, of the days that are in this high sediment load, are atmospheric rivers. So this isn't the 80% sort of number that we were working with earlier, but still well over half of the high sediment load days are atmospheric rivers. And what are the others? They're almost all big snowmelt days. So they come later in the year after the atmospheric rivers have already passed. On the other hand, we've done studies all over the West Coast to ask how much of the total precipitation and total snowpacks are associated with atmospheric rivers, and it's almost half of all the precipitation and snowpack on the West Coast, anywhere from 30 to 50%, is associated with the relatively infrequent atmospheric rivers. So although Dale mentioned this, that although these are big catastrophes, they also are a really big, important part of our water resource. And in that sense, you could probably split that down the middle more or less and say, well, okay, so another 3% were atmospheric river water, but it just showed up later. So these are a big player in getting sediment into the lake. And then there are two stories as to what happens with respect to the clarity of the lake. This is all the Secchi disk measurements, from 1968, water year 1968 on. So you often see these plotted in terms of annual averages and the like, but this is all the measurements here. They're about roughly every 2 weeks, 10 days to 2 weeks. They're done, although it varies through time. And one of the things we can do is look at days when there are very large changes from one day to the next. Not from one day, from one measurement to the next. So this is kind of looking into this to see when you get these big changes in this clarity of the lake, sudden changes. All right. And when we do that, sometimes the differences from one Secchi disk measurement to the next, which is, as I say, on the order of 10 days to 14 days apart, will be greater than 10 meters difference in the change in the Secchi disk depth measurement of clarity. And so we can look at the cases where the clarity, where water suddenly clears up, where clarity increases. And so I took the 15 largest such jumps from one measurement to the next and looked in clarity increases, and all 15 of those were preceded by stormy conditions. That might seem like a small bar, okay, so you get storm and it gets clear. So if I look at the other direction, the largest of the clarity decreases when the Secchi disk can't go down as far before you lose sight of it. All of those were preceded by basically very much not stormy periods where high pressure cells had set up that either diverted the storms away from Tahoe or sat there and kind of basically prevented storms from reaching Tahoe one way or the other. So, just that we know, so stormy gives you an immediate increase, the largest storms give you an immediate increase in clarity. The largest storms give you prolonged periods of without storms will tend to drive you towards decreases in clarity. And of course, by the way, of those 15 cases where you get the big increases, 11 of those were atmospheric rivers. So again, atmospheric rivers play just this lion's share role in these mechanisms, many of these mechanisms that we're particularly interested in the Tahoe Basin from an environmental standpoint. But that's sort of the immediate response. But the other thing, the thing that drew me in was when Dale came to me and was concerned. This diagram, which is at least the cyan-colored bars coming here, is based on the Turk data here. And it's just plotted a different way. And basically, the big question was in 2010. There was the Secchi disk depth jumped up a bunch. And there was a concern that that point right there might indicate a sort of reinitiation of the long-term trend in loss of clarity at the lake. And the question was, okay, so what's the fact that this was actually a pretty astonishingly large year in terms of number of atmospheric rivers, an explanation for part or all of that jump. Okay, so this you can kind of look at, and I know that some people I show this to, and they say, oh yeah, there's a relation there. For me, I have to plot it this way, which is the number of years, the number of atmospheric rivers per year versus the Secchi disk depth. Okay? And when I do that, I get this relation. And it's a relation where when there are relatively few atmospheric rivers arriving in California, Central California coast, the Secchi disk depths are lower, more clarity of the lake. And at this end, where there are many more of them, twice as many or even 3 times as many of them, the Secchi disk depths are higher. Secchi disk depths are higher, so less clearly. That's the opposite of what I just told you when storms arrive. However, and I got to tell you, we don't exactly understand. I don't really understand the workings of that too well. I'm pretty sure what's going on is that when you have these years with lots of these storms, you are getting sediments into the lake. I showed you some reasons to believe that. You're getting a lot of water and nutrients and the like into the lake from the sides. But the immediate influence is either mixing from below or literally dilution of the upper parts of the lake. But you've dumped all this crap, if I can use the technical term, into the lake, and over time you pay the piper for that. The lake, you end up reducing the clarity of the lake. So there are these 2 time scales going on. I think in the interest of time, I'm going to push on and just say, so there are these, so atmospheric rivers play what seems to me to be a really major role in a number of the processes that we worry about a lot with respect to Lake Tahoe itself. I'll just say that. Now, the question I generally get at this point is, well, what's going to happen in the future? And one of the things we can do, atmospheric rivers, the term itself was coined by a group that wasn't looking at satellite data, and it wasn't looking at data they got from weather balloons or something like that. They were looking at weather models. And they noticed that there were these narrow bands in the weather models where all this vapor was being transported. So way back 15 years ago when the term itself was coined, we already knew that these things show up in weather models and their close cousins, climate models. Climate models, the sort of thing that are used to project what happens if you keep putting greenhouse gases into the atmosphere, what happens under climate change. And over here, I'm just sort of illustrating, this is what they look like in a particular data set based on observational records. So this is the real world. And then here's a couple of, so this was a particular day, 12th of December, 1995. There just was one, and I picked it out as an example of what they look like in the real world. Using the same data, but from climate change projections, here are 2 examples from 2 different climate models. This one being from Princeton, and this one being from the Max Planck Institute in Germany. So very different models. And this one is in January 2100, and this one is in December 2090. So what I've done here is just gone out to the end of one of these climate change projections, out to the end of the 21st century, in a couple of the models, and look to see, do we still see atmospheric rivers? And we do, okay? So we see them in the climate models, and we see them even in the midst of climate change. And for this study, I looked at 7 different climate models under a greenhouse gas emissions scenario that involved, instead of us leveling off our emissions over the course of this century, us continuing to accelerate the growth of our emissions all the way through the century. And what we find ultimately is a general increase in both the number and the intensity of atmospheric rivers arriving on the Central California coast in these models. That's over, like I said, 7 different models. We sort of throw lots of models at it in order to try and avoid believing any one model too much. They're warmer at the end of the century by about almost 2 degrees C, and that amounts to roughly 1,000 foot. That would amount to about 1,000 foot rise in the snow line. That's what that would translate to. The increase isn't that large on average. It's 10% more per year, which is to say 1 or 2 more per year arriving. And the intensity, the amount of water vapor that they carry, is probably 10 to 15% more. If you're worrying about, a flood or something, you don't want another 10 to 15% more, but it's not run for the hills ARkStorm. Okay. However, this is hopefully the geekiest figure of all, and what I'm doing here is just plotting a histogram of all of the atmospheric rivers that arrive in several time periods in 7 different models and in observations. Observations, I don't have the future period. And my whole point here is that if you look at these, on average, so different colors are different time periods, with the blacks being the historical period and the other colors being the future periods. And on average, you kind of picture where the average of these different histograms might live. They're not changing that much. Like I said, 10 or 15% maybe. But as it happens, if you plot everything up and look at it, in every one of these, you see these, the average might not change much, but in every single one of them, there are examples of atmospheric rivers towards the end of the century that are anywhere from 50% to 100% larger than anything that happens in the historical simulations by the same model. The historical simulation I'm comparing to, in each case, is a 40-year period. So give it 40 years to pop off a really big one. In the climate change period, I'm giving it 20 years. So I'm giving it twice as much chance in the historical periods to come up with one of these big ones. And in all 7 models, what we saw was this tendency to actually pop off a big one or more some big ones that are bigger than anything that you simulated during the historical period. That's not proof that these things will become a lot more common and that sort of stuff. This isn't a large sample size, that sort of stuff. But it's really unsettling. And it suggests, it suggests we need to study more, which I'm working at, but it also suggests that, at first glance, it seems like ARkStorms, the largest of the atmospheric river storms, might become more likely with climate change. So now I'm just really quickly going to show you what I think an ARkStorm at Tahoe exercise could look like. Dale showed you what the sort of things we did at the state scale and at various places within the state. But this is what I think an ARkStorm at Tahoe exercise could look like. First of all, note these are data we pulled out of the original ARkStorm. And we're looking at precipitation on the top for the 23 days of the scenario. And the amount of runoff that was generated on the bottom. The red ones are days that are warm enough they really don't go down below freezing. The blue ones actually get down below freezing for at least part of the day. And what we see is, so this is just yoinking out the stuff right over Tahoe, more or less. And what we see is that how ARkStorm, the one we have in our pockets right now, looks at Tahoe is it's two storms end to end. Dale described that. The way it worked out at Tahoe is that you get this long, in the first one there's a long period that's actually quite wet, pretty wet, on the order of 2 inches per day on average of precipitation, and cold. So you're laying down a lot of snow, okay? There is a gap as the two storms are, as we kind of stitch the two storms together. And then you go into the second phase, and it's warm. It's just dominated by warm. So we've set down a big snowpack, and then we start dumping lots of water on this thing, looking up to 4 and 5 inches a day of precipitation. That 4 and 5 inches a day will only go up. This is with a pretty coarse scale model. It doesn't see all the steep slopes around here as well as it should. When we run the ARkStorm through what we call downscaling, a regional weather model that knows more about the topography here, those numbers only go up. That's just a fact. There's no way it's not going to. So that's what Tahoe. So that ARkStorm Tahoe is a wet sequence that does have lay down a bunch of snow and then lay down a lot of rain, warm weather and rain. Not a good combination for Tahoe. I think the title of the entire talk was sort of impacts at Tahoe, ARkStorm impacts Tahoe. Here's some list of my thoughts, and these kind of fell in line with the meeting we had today. I don't think I saw any particular surprises, but there are these short-term impacts. This is more or less during the storm and immediately afterwards. There's flooding along the streams and in meadows, wind damage, wet snows, traffic interruptions to and from, both around the lake and to and from, infrastructural damages, utility interruptions, trashed snow runs, erosion. So these are sort of the people impacts, and then some of the more environmental impacts down here. Remember that we saw this funny dilution of the lake in the short term to be followed by paying the piper in terms of clarity later on. I should say, that all the exercises that we've done to date have been down in the lowlands, San Diego, Ventura, NASA facilities, the Navy facilities. We've been struggling with the Bay Delta, that sort of stuff. And this would be our first experience with this, really running through these impacts at the upper elevations in a place where this column matters about as much as this. Very often the ARkStorm exercises we're dealing almost strictly with emergency responders. And they're all about this stuff. This is something somebody will worry about after the storm goes away. Okay? And then also, because we've been working down in the lowlands and because we've been working mostly with emergency responders, they are very much focused on what's happening during the storm, giving people safety, that sort of stuff. And the longer term impacts are much less on their minds. But at Tahoe, I don't see how you can get away without thinking about the longer term impacts. So Dale described ARkStorm as a 1969 storm sequence stitched together with a February 1986 sequence. And any of you who have been around since 1986 may remember that 50 was closed for several months. 80 was closed for a few days. The Truckee River basically eroded away and carried off sections of the natural gas pipeline. So everything in South Reno down through Gardnerville, maybe beyond that. I was living in Carson City at the time. Was cut off from natural gas for several weeks, there are long-term impacts to this. It's not just a matter of getting people out of harm's way. There are long-term impacts, and we know that for this part of the world. So you see the list here, again, sort of continuing traffic interruptions. For instance, as I said, in 1986, 50 was closed for, I think it was 3 months. It was approaching 3 months, if not. It was a combination of a major avalanche, snow avalanche, but also landslide just carried away or buried quite a chunk of it. Yeah, you guys have probably already read this stuff. And then the environmental impacts start to mount because they take a while. It's, you know, in part they take a while, and so again, you know, that's an element of ARkStorm at Tahoe that's really attractive, is that you can get beyond the emergency to the longer term impacts and really start to think about those. And I should say, during an emergency, it's really not a good time to be thinking about what the long-term environmental impacts are going to be. The right time to think about that is before the emergency, and to actually decide which are the ways that we want to deal with major emergencies. That you know, if we've got two different ways, and one of them is going to have dire long-term consequences, and one is going to have short-term consequences. Gosh, we want to know that. We want to know, and maybe we can lean more towards the one that, the option that reduces the long-term impacts. The way these things end up working is that we string together bunches of models, fundamentally. And this is a total messy-looking thing, but we've done this stuff here. So meteorology models all the way down through urban runoff and erosion and nutrients and the lake clarity model, that sort of thing. We did this recently for a climate change assessment that Bob Coates led. So we know about linking together models at the lake and you know, pulling together these stories. We need, you know, there are other elements here that we'd be sort of struggling with. For original ARkStorm, you know, we worked with engineering models that allowed us to estimate wind-driven damages and the like. And so some of these we can pull from other parts of the world that we didn't necessarily try out for a climate change assessment at Tahoe. Well, we cascade these models, and fundamentally what we do is, you know, we do a bunch of cranking of numbers, and we end up with a bunch of numbers, maps, and stories. That then what we do is we take to a series of local expert panels. And here I've listed a bunch of the kinds of people that we bring in. With the original statewide Tahoe, we had 12 different panels with over 84 or something, I don't know what the number was, different experts that we brought in to walk through. We showed them the ARkStorm scenario and results from all this modeling stuff, and then walked with them through what the consequences, what they believe the consequences would be in their sector, whether it be you know, power and telecoms. You know, we would talk to them and we would sort of chase these things through and come up with the most plausible, not necessarily predictions, but the most plausible outcomes of this kind of storm and its various consequences. And you work with a bunch of economists of the sort that we worked on the statewide ARkStorm and policy wonks to come up with nice dollar figures that really help. And then we end up by running or organizing a big summit where we bring lots of interests together to talk about the risks associated with this kind of major storm, what kinds of responses are doable, where there are weak points in terms of our emergency responses, that sort of thing. Planning for, you know, sort of proactive stuff to try and reduce, to avoid turning a disaster into a catastrophe, and the like. Let me see. And so that's sort of my vision of how we ought to go about and do an ARkStorm at Tahoe exercise up here. And I've described to you several reasons why I think it's particularly useful from my perspective to do it at Tahoe. You who live up at Tahoe, you know, this is hopefully kind of real to you in a sense, so that, you know, maybe you don't need my little motivations of let's let's think about the long-term impacts, that sort of thing. But yeah, I believe I'm stalling because I think the next slide, yeah, is where I end up. So yeah, so basic point is here's our emails, that sort of thing. We continue to work with people around the state on ARkStorm consequences and exercises and the like, and actually I'm involved in a proposal to try and cook up essentially an ARkStorm in the Pacific Northwest currently. So this is an idea like Shakeout that has its own traction, but I'm really hot on the notion of doing an ARkStorm Tahoe, and I hope that sort of motivated you guys to think we ought to too. Thank you.
Regional Hazards Coordinator for the USGS Pacific Region and Region 9 Chair of the Department of Interior Regional Emergency Coordination Council. Try to say that 10 times fast. Michael Dettender, we'll call him Mike. Mike is a research hydrologist for USGS and a research associate at the Climate, Atmospheric Sciences and Physical Oceanography Division at the Scripps Institution of Oceanography. Try to say both of those fast. So yeah, so let's bring them both up with a warm round of applause.
Mike Denger's shy.
No. Just, I'm not talking until later.
Yeah.
Okay.
So we'll start
I wanted
with
to see
Theo.
your size.
Pop that in.
Can you hear me? Yes. Try to. Now, I have massive PowerPoints, so this PowerPoint is like 350 meg. It's bound to crash. Just going to tell you this right now. I'm here to talk about ARkStorm, and ARkStorm is a scenario, but first I need to talk about what it is that we do at the U.S. Geological Survey. And really the USGS doesn't manage or regulate anything. We just basically provide sound science to the public, to policymakers, and people that have to make hard decisions, and hopefully that science holds up in court and carries the day, because what I'm focused in and all this stuff here is the natural disasters. One of the things that we really work for is to save lives and property. A little bit about multidisciplinary science, and I have to do this because I've been spending the last 15 years doing this, is trying to bring science together within the USGS. I've seen a couple of scientists here, and they can tell you that science tends to stovepipe, you know? I mean, you're working as an ecologist in alpine systems, and you're going to be around other ecologists in alpine systems. And I had to cross the divisional lines, and in the USGS, they were really divisional lines. One of the first big projects that I did up here was the mapping of the bottom of Lake Tahoe. And that was to bring in our scientists that do oceanography, to bring up Dr. Tahoe, really to give the ecologists a better idea of what's down there so that they can know where fish live and many other good things. But then the next thing that I did was, gee, what happens when you take up concrete in the LA River? I mean, LA, you've probably seen Arnold Schwarzenegger driving down the aqueduct system there in his motorcycle, or if you're watched Grease, etc. This place is as dry as a soda cracker. You start reintroducing tertiary treated wastewater in this system, and you might have liquefaction in the event of an earthquake. You might be reintroducing these pharmaceuticals and drinking water into an aquifer system, and there's a lot of issues that you need to deal with. And she is a major star, because if there's an earthquake, you turn on that television, and who's going to be there? You're emotionally invested in this whole ordeal, and this is the woman that is talking to you. She's one of Time's 50 most influential women, and she is the leader of this. I was a project manager on all of these things, and a superior staff scientist, and we have a whole list of people that were participating in this, that were dealing with the physical aspects of it, the engineering, and then the social and economic concerns. A lot of people. So, an earthquake scenario, at its very least, this is an earthquake scenario. This is the type of shake map that you will see after an earthquake. Within 5 minutes after a major earthquake, hopefully you won't see one that looks like this, but you'll see in the Mercalli scale, and it'll have in there how much peak ground acceleration and all that, but you don't really care. All you need to know is this red here, that is enough to bend steel rails. Okay, so that is some intense shaking. And so this blue here, that's the P wave. That's the one that when it hits you go, oh, hey, was that an earthquake? That's kind of cool. Okay, so we had to pick an earthquake. In the scenario, we picked a 7.8 earthquake. That means that this area of the fault had not moved for about 300 years. So this area down here, this had moved in about 150 years. But every section of the San Andreas Fault tends to move in about every 150 years. So this would be a good one to pick if you're going to pick one. Now, we chose it to happen at 10 o'clock in the morning. Why did we choose that? Because everybody would be working that day. This is going to be in a third. There's really one geared for a USGS that deals with geology, water, biology, and geography. So, natural hazards in the Pacific region, the regional hazards coordinator. Most of this stuff is dealt with. And by the way, I don't have volcanoes up here. I've left that out for some reason. I don't know why, because it's a big issue for me right now. But it's earthquakes, fires, floods, landslides, debris flows, tsunamis, coastal change. The Pacific region is California, Nevada, Hawaii, all the way out to the Pacific Islands in Guam, Kwajalein, etc. And there's a lot of stuff that we do as a matter of course. If there's an earthquake, you can go on our website and you can see exactly where that earthquake happened, where the shaking occurred, and how many people were affected, the economic hit, and how many fatalities could happen. And then we give you that information within about 15 to 20 minutes. That's a pretty good deal if you're an emergency manager. You know where to go and you know not where to go. So this is a really good idea so that we turn this into a multi-hazards approach. And we started by the way, this ditch is what, 6 geologists high? Okay, that's weird. Okay, we brought all these emergency responders together and say, hey, how can we have science help you? You know, and they kind of look at each other and they're like, well, we're not scientists. We don't know what you guys do, and you know, unless we're scientists, we don't know. And so this guy here, Larry Collins, he's the captain of Los Angeles County Fire Department, Urban Search and Rescue. A very photogenic guy, as you can imagine, in LA. And he says, you know, we do disasters as a matter of course. It's the catastrophes that take us by surprise. If you could help us with the disasters, we'll do the catastrophes that much better. Or, no, if you do help us with the catastrophes, we'll do the disasters that much better. And I got that, because I think I crafted that quote for him. I said, come on, do it again, you know? And he was the one that says, you know, everybody talks about the big one in Southern California, but I've never actually worked a big earthquake. I mean, I went down to Mexico, and you know, they had me do here and here and here. But we had all these young guys, and then you know, we had the older guys who worked on Northridge who think they know it all. But really, Northridge only was an earthquake that occurred if 7 seconds of shaking. A 7.8 would take about 2.5 minutes. I mean, this is a big deal. If you were talking about this room shaking that much, I mean, you would have this thing here, and then a second later over here, and then back again over here. You know, I mean, it'd be like that for 2.5 minutes in some areas. So they aren't really prepared to deal with that. So what we decided to do was to put together an earthquake scenario, and then also look at the fires. And so we coordinated the Southern California firestorm. And then also put together a tsunami scenario, which is still going on, and then a winter storm scenario. But the first thing that we did was the ARkStorm, the shakeout scenario. Now I got to tell you, the fearless leader of this is Lucy Jones, and if you go into Southern California, there's stars everywhere in LA, but you walk around with Lucy,